my pleasure to introduce Professor Scott Moura. So Scott Moura is an assistant professor at the University of California, Berkeley. Hey, look at that. In civil and environmental engineering. He's also the director of eCAL, faculty scientist at Lawrence Berkeley National Laboratory, and PI at the St. Paul Berkeley Shenzhen Institute. He received his PhD from University of Michigan in 2011, where he also got his master's degree, and his bachelor's degree he got from Berkeley in 2006, all in mechanical engineering. He was a postdoc at UC San Diego in the Cymer Center for Control Systems and Dynamics, and a visiting researcher at the, here we go, Centre Automatique et Système, I don't know, at Mines Paris Tech in Paris, France. He is a recipient of the Oak Hugo Schuck Best Paper Award and a Carol D. That's a site. Soch, distinguished graduate student.
Carol D. Soch.
Okay. And I also would like to mention that he teaches 2 courses in rotation right now. One of them is Design of Cyber-Physical Systems, which I believe is in the fall. And one is Energy Systems and Controls, which is in the spring. And just quickly, I'd like to say that I took that course and it was awesome. So with that being said, please welcome Scott Moura.
All right, thank you all for having me. It's a great honor to be here. I think it's, today I've been able to tour the nuclear engineering labs, and Chris and I are joking that although I did my undergraduate in this building, I'm seeing things and hearing about research that I didn't know exists, and it's so cool. So thank you for kind of inviting me into your community to share some of the research. So I'm going to talk about batteries, yes. However, my goal is that you can look at this and think about how in your area you may have some sort of, let's just call it a process system, for which you would like to model it, you would like to identify parameters, and you may be interested in doing something specific like diagnosing when faults occur, when something bad happens. Okay? So I'll talk about specifically in the context of batteries, because that's the application we work in our lab, but really I'm trying to highlight the methodology. So first I need to highlight the ones who have actually done this research. This is the team that has been supporting the battery research. So in particular, a lot of the research on the identification has been done by Sehong Park and Zach Ema. And let's see, Dylan Cato, who's here. And then in the last part of my talk, I'll talk about fault diagnostics. A lot of that work has been done in collaboration with Dr. Satadru Day, who is now a professor at the University of Colorado. Okay, so I'd like to say that we live in a golden era of batteries. They are pervasive. They exist in everything from, heart implanted pacemakers all the way to consumer electronics. They're enabling electrified transportation, solar aircraft, an incredibly interesting area, all the way to grid-scale energy storage. What I'm plotting on the right is a histogram for the number of publications where you search keywords battery systems and control. So I work in systems and control, and what you can see is that during 2 decades, from roughly 1985 to 2005, it was basically dormant. This wasn't really an area of interest in academia. And then something changed right around 2004, where there was the first paper that described how to do state estimation for batteries, specifically using extended Kalman filters. Actually, it was a triplet of papers by Greg Plett out of the University of Colorado Mines. And ever since he started that, this field has absolutely exploded. And you can see that from the data. Of course, the numbers aren't fully in from these last years, which is why you see that dip. I mean, it's expected that it'll continue to rise. So it's a rapidly growing field. Now, of particular interest in managing this particular system are failures. So this is something that we definitely want to understand well, and we would like to mitigate against. So 2 of the famous examples are, for example, the Boeing 787 Dreamliner. You're all probably familiar with the fact that a number of those planes were grounded due to battery fires that emerged. Actually, one of our PhD students who has now graduated worked at Boeing during that period. And if you flew in an airplane in calendar year 2016, then I'm sure you've heard the fact that you cannot have a Samsung Galaxy Note in your pocket or on board. So it turns out that a lot of these disasters could have been mitigated with some sort of form of fault diagnostics. And as it turns out, what was used in these industries was extraordinarily primitive. So we're interested in how could we build a science in mitigating these sorts of disasters in a battery context. Okay, so let me first highlight just the general battery problem. So I'm just going to give some background on battery management systems and batteries in general. So we want them to be cheap. We want them to have high energy and power density. We want to charge them fast, and we want them to live a long time. The reality is that they're way more expensive than we'd like. They're conservatively designed and operated because we don't fully understand how they work. And they die quicker than we'd like. So here's some motivating facts around batteries as energy storage systems. So if you think about batteries used for electrified transportation, the cost of batteries has been increasingly coming down. So in 2010, it was something like $1,000 per kilowatt hour. Today, it's getting, the last numbers I heard were dipping below $200 per kilowatt hour, maybe down to $150, depending on what context you're talking about. It turns out that if you're interested in electrifying transportation, the magic number to get at is $125 per kilowatt hour. This is the number for which the battery and the electric motors are on economic parity with an internal combustion engine, the IC engine. So at that point, economically, it doesn't make sense to combust fuels for transportation. The problem with batteries, among many, are that it turns out that because we don't fully understand how they operate, we're conservative with how we use them. We may use, in practical applications, only 50 to 80% of their true available capacity. Another related aspect is, of course, this limits range. It causes range anxiety in the context of electrified vehicles. And then there's lifetime risks caused by fast charging, which could lead to things like the fires that we saw on the previous slide. So there's a really excellent study that is published in Nature Climate Change where they did an excellent techno-economic analysis of the decreasing cost of batteries, for which the U.S. Department of Energy set this target of $125 per kilowatt hour. This is now a little aged. Let's see, the study was published in 2015, so they had data from 2014 and older. However, it looks as if we are on this trajectory to meet that target. So that's really great news in terms of the cost per energy. Now, part of that comes from manufacturing, right? As we grow the supply chains in this, we can decrease costs. So, for example, you have this famous individual who is creating the largest manufacturing plant in the U.S. by square footage, and that'll certainly help to bring manufacturing to bear on this problem. But there's a lot more we can do in terms of science and engineering. So I like to say that there's really two solutions to helping achieve these goals. One is to design better batteries, and one is to make current batteries better. Right? So a little play on words. What I mean by that is designing a better battery is really a question of material science and chemistry. Finding that next new chemistry that has greater energy storage density, greater power density, so on and so forth. Incredibly important work. We are not in competition with that. In fact, we support it and enable it. But the other side of it, which is often not given as much credit, I think, is making current and future batteries better, which is really a question of the automation, the controls. How do we ensure that we can maximize the performance and safety of these devices? So that's the area we work on. And the ongoing research goals in our lab are the following. So, I tell my students they can't graduate until they hit these metrics. Okay. So things like increase usable energy capacity by 20%, decrease charge times by a factor of 5%, increase battery lifetime by 50%, and decrease fault detection time by a factor of 10. So I'll eventually, in the last part of my talk, get to this last point of how we're able to accomplish that. Okay, so first let me give some background on batteries. and some fundamentals of electrochemistry, so we can understand this electrochemical process. So, history. Let me bring you to the 18th century and the north of Italy, where we find Luigi Galvani. Luigi Galvani is a physicist and a biologist, and he did this now famous experiment where he took a dead frog, connected it, and found that the moment when he connected these two frog legs to these two basically alligator clips, the frog would jump to life. So at that time, he found this incredibly interesting. Why was it jumping to life when he connected the frog legs to this metal? So he theorized that there was something that he called animal electricity. There was some internal energy source in this deceased animal, right? And that it would, come to life when he connected the metal to it. And so, like academics and also like Italians, they like to feud with each other as they sort of debate on ideas. He eventually presents this idea in front of Alessandro Volta, who sees this and says, I don't think it has anything to do with the animal physiology. I think it actually has to do with the fact that he's connecting two dissimilar metals in a particular way. So Alessandro Volta, to test his idea, comes up with what is known as a voltaic pile, where he takes zinc and copper, and between them he puts this electrical insulator, but it allows ions to pass through it. And voila, he created the first battery. He was able to measure voltage across these two metals. In high school, has anyone done the experiment of putting a zinc-coated nail and a copper penny into a lemon, and you can measure voltage? Has anyone done that experiment? All right, well, you are recreating Alessandro Volta's voltaic pile. That is exactly what it is. Of course, volt comes from his name. So that was the first battery. Today, we have a whole zoology of batteries. And what I'm showing here are all the different breeds of the lithium-ion chemistry, particularly those on the cathode. So these are radar plots or spider diagrams that kind of describe the various aspects and features of these different cathode chemistries. I'll highlight just a couple here. So the ones that were in those batteries that caught fire were lithium cobalt in both the Dreamliner and the Samsung Galaxy Note, I believe. NMC, nickel manganese cobalt, is particularly popular, especially in the automotive industry. You can see it basically has no weakness. It kind of is strong in all areas here. Lithium iron phosphate is another interesting one. It has low specific energy, but high lifespan, high specific power. These things are pretty bulletproof from a safety point of view. So there's a whole zoology of these, and these aspects are how people characterize these different batteries. Let's see what I have here. I think I brought something to play with. These here are lithium nickel cobalt aluminum. So I'm going to pass around these green cells here. You can take them out, pick them up, kind of feel how heavy they are. These are essentially the ones that are used in the newer Model S. Okay, Tesla Model S. Okay, so let's talk about what are the estimation and control problems in batteries. So first we need mathematical models to describe the physics that occur in batteries. The first category of models are known as equivalent circuit models. Now, these are so-called phenomenological models. What they do is they really try to mimic the voltage current behavior of batteries, the input-output behavior of batteries, by hypothesizing that there's an equivalent electrical circuit that mimics that behavior. Now, if you crack open those batteries, please don't do it right now, we're going to create a mess. No, you can play with them, just don't bring them open. Right? They are not composed of resistors and voltage sources. They are electrochemical systems. Nonetheless, the people who do battery management systems think about them in this way, and you can get progressively more complex circuits that kind of incorporate more of the dynamical behavior. Frankly, I think the reason that the industry is attracted to this is because the engineers that are responsible for making these battery management systems are electrical engineers, and they're comfortable with thinking about things as circuits, right? And less so thinking about them as electrochemical systems. Those people are designing the materials, not the battery management systems. So here's where our lab comes in and says, no, because we're really concerned about getting high performance and safety, we want to explicitly model the electrochemical, thermal, mechanical phenomena that occur inside these batteries. So let me walk through roughly how a battery works. Okay, if I borrow one of those? Sure. So if you take this cell and you take a pipe cutter, for example, please do this in an argon glove box, and cut this open, then what you'll find is that it's actually composed of these sheets that are all wound up in what is commonly referred to as a jelly roll. And then they put it in this aluminum can here. Okay? Now, 3 of these sheets are respectively the anode, separator, and cathode. So the drawing here is a cross-section through these 3 sheets. Right? So the anode and the cathode are essentially two metals that are dissimilar. And they're dissimilar in a very specific way. They're dissimilar such that as lithium ions flow from the anode to the cathode, there's a release of Gibbs free energy. And specifically, when the battery is fully charged, lithium will be diffused in the interior of these particles that make up the structure of the anode material. And when you discharge the battery, the lithium ion will diffuse from the interior of these particles to the surface, undergo an electrochemical reaction where it splits from Li to Li plus and an electron. Very simple. The lithium ion is now in this electrolyte, which you can think of as like a soup, a liquid, if you wish. And it transports from the anode through the separator to the cathode. Because the separator is electrically insulating, the electron is not allowed to pass with it. It is forced to go through this external circuit to power your device, drawn schematically by that light bulb. It meets back up with the lithium ion here, undergoes the reverse electrochemical reaction, and diffuses into the interior of this particle. That is the basic phenomena that occurs in a battery. So we would like to track that behavior amongst other things. Now, why do we care? We care because we want to move from the paradigm on the left to the paradigm on the right. Namely, the way we think and operate batteries right now is simply putting limits on what we can measure. So I can measure electrical current, I can measure voltage, maybe I can measure temperature on the cell. I'm going to put upper lower limits on those, and that's my operating envelope. But in reality, if I actually understand some of the internal variables, which I can't directly place the sensor on, those things relate more to the fundamental limits of the battery. So imagine for a moment that I've got a magical sensor, some way where I can estimate well or sense well those internal variables. If I can, then I can potentially expand the operating envelope. Right? Actually, it's not just, I'm not just saying that the red set is a subset of the green. There are actually certain conditions where, for example, your voltage seems to be in bounds, but there's some internal variable that's out of bounds. That often occurs when you fast charge, for example, in cold environments. That's one case. So really it's about, if I can understand what's happening internally, I can have higher performance and guaranteed safety. That's the point. So then the game is, how do I understand what's going on inside? So for that, I need mathematical models. Now, if I have good mathematical models, then I can come up with what we call an electrochemical controller. So this is automation of my battery cell. So I have my physical battery cell, like the one that's being passed around. There are things that I can practically measure, like the current I apply on the battery cell, the voltage and temperature response. And then from that, everything in the dash gray box is in software. That's the automation piece. So for example, I may have some electrochemical-based model-based algorithm, which is state and parameter estimation. So I'm going to estimate the internal states and parameters. That's the monitoring piece. Now, once I can monitor those, then what? What do I do with that? Then we have the automation piece, which says, okay, now I'll feed that to an electrochemical model-based controller, which says, all right, here's a safe way to apply current that ensures I can get maximum performance while ensuring safety. So this is like the one big picture, throw it in a patent. This is what our lab does. Okay, so let's talk about the electrochemical model for a moment. So now we're going to get into the modeling piece. So here's a schematic of the lithium-ion cell where we cracked it open. You can see the different layers here. And what I described to you is a fundamental process of how lithium ions, the story that they have as the battery discharges from 100% SOC to 0% SOC. And this the mathematical model that I'm going to present was actually first developed here at UC Berkeley by John Newman, who is a professor in, who is still a professor in chemical engineering. I guess he's a professor at the graduate school, as they say. His model actually has kind of spurned a lot of this research that's doing electrochemical model-based control. So let me give you an idea of this model. All right, now I'm showing a lot of equations, and my intent is not to explain these equations to you. Rather, it's just to give you an idea of the mathematical structure, so you can appreciate the phenomena, the physics that could be in here, and the mathematical complexity. Okay? So, first, let me just highlight that we're interested in the concentration of lithium in the solid phase and the electrolyte phase, which is represented by these two partial differential equations up here. So the point here is that we have two partial differential equations. The first one is in spherical coordinates. The second one is in Cartesian coordinates. It's essentially the heat equation, but nonetheless, we're dealing with PDEs for the dynamics of lithium concentration. In the next three equations, we have ordinary differential equations in space. So you'll notice that we have Vs, Ve, and IE. Those are the variables that are important here. But you notice the derivatives in x. These are ordinary differential equations in space. Right? So I have PDEs in space and time, and then now I have these ordinary differential equations in space. By the way, these essentially model a distributed parameter version of Ohm's law. It's essentially just Ohm's law on steroids here. Then you have this kinetic reaction. The point I want to make here is simply it's a nonlinear algebraic equation. Okay? So we have PDEs, ODs in space, a nonlinear algebraic equation, and finally we have some temperature dynamics. So capital T is temperature. We have an ordinary differential equation in time, and this is our model. So, for someone doing systems and control, this is really exciting because it's like as complex of a model as you could possibly encounter to be able to do something with. But it's incredibly complex, as you can appreciate. PDEs, ODs in space, ODs in time, nonlinear algebraic equations. Nonetheless, we've developed a simulator model for this. And here's an example so you can appreciate what are the dynamics in a battery. So I've arranged this figure so the anode is on your left and the cathode is on your right. The separator is in the middle. On the top, we have the concentration of lithium in the solid phase, and on the bottom, we have the concentration of lithium in the electrolyte phase. So here's what's going on. On the top, we have two dimensions. We have this x dimension, which is how lithium varies kind of along the thickness of these sheets. And then we have the concentration along this radial dimension r. That's the concentration of lithium as it goes along the radial dimension of those particles, these spherical particles. Okay. So what you can see here is that there's higher concentration in the center and then lower concentration at the surface as lithium leaves these particles, and then it enters into the electrolyte, undergoes diffusion and transport to get to the cathode here. And then you can see here that there's a higher concentration at the surface, particularly at the separator cathode interface, and then it gets lower as you go towards the center there. Okay, so that's the mathematical model. So far this is all kind of theoretical. We would like to match our mathematical model to the batteries that are being passed around here. So this is the model identification problem. So here's the objective. I would like to identify the parameters of my mathematical model from experiments. So specifically, given measurements, in my case for the battery, given measurements of electric current, voltage, and temperature, I would like to identify uncertain or unknown parameters. Now there's two main challenges here. The two main challenges are, how would I design my experiments? How do I excite my process so I can easily identify these parameters? Very interesting question. It's an optimal experimental design problem. The second question, and probably the slightly easier one, is once I've collected that data, then how do I optimally fit my three parameters to that data? Okay. So this is what I want to discuss with you next. I imagine you guys have situations where you have a physical process and you would like to identify a model from data. So, we spent a long time reviewing the literature on this. This is the specific literature for batteries. And, we spent time thinking about what are the models they use, what sort of optimization, what sort of algorithms, experiments, blah, blah, blah. Here's the key takeaway point, is that we found that typically experiments are not optimized for parameter identifiability. In other words, you may run some experimental profile where it's a standard experimental protocol, but you have no idea if that protocol is the best for maximizing the sensitivity to your unknown parameters. So that's the issue that we really wanted to address. So let me give some background on, I think, what we thought was the right tool to think about this. So my background is in control theory. That's, I took 10, 15 classes on that area. So I thought about this and said, this is really an optimal control problem. Let me explain what an optimal control problem is to convince you that optimal experimental design can be thought of as an optimal control problem. So the situation is this, my objective is to optimize the input of my system. So U is the optimization variable of interest, where I would like to optimize this controlled input to minimize some objective function. In this case, I actually want to maximize sensitivity to my uncertain parameters. Now, the reason it's an optimal control problem as opposed to just a plain optimization problem is because my system is subject to dynamics, which I'm representing by this standard nonlinear ordinary differential equation. Okay? So, and it's an optimal control problem also because my optimization variable here, U, is actually a trajectory. It's not a finite number of points, right? It's actually an infinite dimensional object. It's a trajectory. So that's known as an optimal control problem, used in a variety of industries, chemical, aerospace, automotive, all the things, many various industries. So we thought this was the right way to think about this problem. Now, there's many ways to numerically solve this optimal control problems. I'm listing some of them. And I want you to keep that in mind for what I'm going to say on the next slide. So we formulated an optimal control problem to design this input U to maximize identifiability. And I'm not going to go through the details of what these equations mean, but basically we have our process here, which is represented by a differential algebraic system that's essentially when you discretize the battery model, that's what you get. And then here are some auxiliary differential equations which model the sensitivity of the states and outputs to parameter variations. Okay, so these are the sensitivity equations. It turns out that if you take S3, which is the sensitivity of your output to parameter variations, and apply this metric, then this maximizes sensitivity to the parameters in the sense of the Fisher information matrix, which is a concept in information theory. Anyways, the point is it's an optimal control problem, and now that I've formulated this, my problem becomes, how do I solve this optimal control problem? That's now what I need to do. Okay, so this formulation is very elegant, it's mathematical, okay? But it turns out this optimal control problem proved to be computationally intractable. Namely, it took us 2 weeks to generate 100 seconds of optimized input signals, which is just not tractable or feasible for us. Let me back up for a moment and tell you that the way that we are presented this problem is one of the major multinational companies came to us and said, we're going to give you these cells. In 30 days, you can do whatever experiments you want to them. You have access to as much computational resources as you want. Identify the parameters of the electrochemical model. You have 30 days, go. Right? So, needing 2 weeks, burning that to get just 100 seconds of optimized input obviously doesn't fly. So, here's our optimal control problem formulation. X that. That just doesn't work for us. So, we needed a totally different idea. And for this totally different idea, I'm going to bring you to a dim sum restaurant. So, here's what I want you to think about. We're going to think about this like we're in a dim sum restaurant where there's a fixed menu. All right? So what I'm going to consider now is that rather than trying to optimize an input profile from nothing, I'm going to a priori create a menu of possible input profiles that I could apply on my system. Okay? So I could have L inputs on my menu. And now my goal is to select from that menu how many times do I want to run this experiment, right? So I've got 1 steamed shrimp dumpling, 2 pan-fried pork dumplings. I really like the egg tart, so I'm going to do 5 of those. That maximizes my pleasure. So, but how do I, so we're going to think about it this way from the perspective of I have a fixed menu, and now my goal is from this fixed menu, determine which inputs would be best for maximizing sensitivity to uncertain parameters. So it turns out that if you do it this way, you can come up with a convex optimization problem, which is essentially like, you can view it as like an OR. They would call this like a knapsack problem. But because it's a convex program, that means you have polynomial complexity in the number of variables. So for one profile, it took me 2 weeks to get 100 seconds. Now that we figured out this idea, we can optimize 750 input profiles in 20 seconds. So this was super enabling from us by just completely changing our perspective. I had to get out of my control theory way of thinking, and now come back to this convex optimization way of thinking. So that was the key idea in that work. Okay, so from that, I'm going to skip all the details and say that after running those optimized tests and then optimizing the parameters, we were then able to get a well-fitting model. So what I'm showing here is a distribution function of the absolute voltage error. So what this plot says is that 50% of the error is 10 millivolts or less. And we thought that was pretty good because if you're using a 10-bit A to D converter and a 10-volt reference voltage, then the minimum resolution on just that equipment is 10 millivolts anyway, so you can't even measure less than that. With that, frankly, that's modest equipment. But so that's where we stopped at that point, or are continuing to work, frankly. So let's now talk about fault diagnostics. So let's come back to this battery safety problem. Now I want to address the issue of how do I detect and estimate when something bad happens. Now that I'm armed with an electrochemical model and I know how to identify it well from data. So we created a list of various battery faults. And in the work I'm going to show you right now, we're going to focus on thermal faults. So these are things like thermal runaway, convective cooling failure, internal thermal failure, and by the way, you can download these afterwards if you want. But here's an example of thermal runaway. So this is a simulation of a battery pack where each of these circles that are arranged in a honeycomb fashion are a battery cell in a pack. And what's being simulated is some fault in this cell. And what you can see is over time, there is a positive feedback loop that occurs which causes this thermal runaway effect. Essentially what happens is when one battery has like a short circuit or something like that and it starts to generate heat, then what the effect that has is it causes the electrochemical reactions to happen faster. It's your Arrhenius type of effect that you expect. When those reactions happen faster, current flows faster. You have I squared R type of heat generation, and that's the positive feedback loop. It's pretty simple to understand. So we would like to detect when this sort of thing happens before we disallow people from bringing their phone on the plane. So here's the objective. I would like to detect a fault when it happens, and more than that, I'm going to add another objective. I don't want to just detect when the fault occurs. I would like to estimate how big it is. Okay, in some sense, estimate the fault size. There's a couple challenges here. One challenge is that we have few measurements. So, and generally in process systems, we can't like paint sensors over everything, right? So we can only measure a few things. And the faults may be occurring away from where our sensors are. The other reality is that we're going to leverage a physics-based model. But as you know, all models are wrong, but they can be useful. So we have to deal with this fact that there's uncertainty in our model. So we have to deconvolve the model uncertainty with a fault. Does that make sense? We have to be able to separate nominal behavior from faulty behavior in the face of uncertainty. Okay, so the state of art in industry, at least for batteries, is limit checking on measurements. What I mean is, you know, if I can put a sensor on it, I can see it, and then I'll just have max and minimum limits on those things I can check. For example, in a battery, I might say, and maybe you've experienced this with your phone, when the temperature gets above 60 degrees Celsius, I'll just shut everything off. Does anyone experience that? Yeah, that happens to me all the time, especially when I biked to a Cal football game on a hot Saturday afternoon, and then I'm texting my friend, and then my phone shuts off. That happened recently. So anyways, we would like a better way than that. Okay, so the other thing is the published literature does not really address internal faults. They address things like your sensor going bad, or you're overcharging and discharging. So that's really kind of a modest thing. I really want to estimate internal faults that are happening in the electrochemistry. Okay, so here's the basic diagram of how fault diagnostics works. So the centerpiece is this diagnostic algorithm, which at the end will give, for our case, a thermal fault information. So there's three pieces that go in here. We have a model. In this case, I'm going to show you a distributed parameter model for the thermodynamics because we're focused on thermal faults. We have some measurements. In this case, I assume I can measure voltage, current, and surface temperature. And then I've got some control theoretic tools that help me with the mathematics. Because I'm trained in control theory, we make a big deal about proving convergence of our algorithms. Okay, so here's my thermal model. It's actually a very simple model. I'm going to look at my cylindrical battery cell, and I'm only going to focus on, I'm going to assume that the dynamics are homogeneous in the axial direction, and I'm only going to think about thermal dynamics along the radial dimension, from the center, from the axis of the cell to the surface. And the model I have here is just a heat equation. That's just diffusion of heat. And then I have heat generation, which is given by Q dot T. Actually, this could be a function of R as well. All right? And then I have, because I have symmetry at the center, I have zero flux through the center, and at the surface, this basically says that the heat transfer at the surface is given by the difference between the ambient temperature and the surface temperature. That's a pretty simple model. I particularly have a background in PDE control theory, so I get excited about the PDEs. Okay, now, we're going to hypothesize that a fault could occur. So, boom, now we have a fault. So delta Q represents some internal heat generation, which is some anomalous thing that could possibly occur in this battery. So I'd like to detect when this thing occurs. So the objective will be to detect and estimate the thermal fault size, and the algorithm that we've come up with looks like this. So first on top, we have this box represents our lithium-ion battery cell, and then this comic book like drawing here says, boom, there's a fault. Delta Q is now creating some anomalous heat generation. But all I can measure is current voltage and surface temperature. And the fault diagnosis module in software is here. So there's two pieces. There's a robust observer, which tries to estimate the internal distribution of temperature. And then from that, I have a diagnostic observer, which detects the presence of a fault. So that's how we've decomposed this. Right. Okay, so now we'll get a little bit into the control side to give you an idea of how the algorithm works. So math is really the enabling thing here. So here I have my system model. I've actually done a slight change of coordinates, so R turned into X. I've done that so it looks like a cleaner heat equation here. But anyways, I have a heat equation, and now I'm going to hypothesize that my thermal fault is given as follows. My thermal fault, I'm going to think about this basis function. I'll call it psi, which could possibly be a function of X, the spatial coordinate, and could possibly be a function of time. And the theta is a coefficient on it. So what I'm trying to say is, what we're going to do eventually is estimate theta. So when theta is non-zero, I've detected a fault. The quantity of that theta will be the size of my fault. Okay, that's why I'm doing it this way. All right, so that's my system model, and I'm going to hypothesize that I can model the fault this way. The robust observer is going to be as follows. So this is something that you can learn about if you take my class CE 295, Energy Systems and Control. We're going to design a state observer. I'm going to, in software, make a copy of my model, but then I'm going to correct it with measurements. So I'm going to take the error between my surface temperature, that's T at X equals 1, and then my modeled surface temperature, which is T1 hat. I'm going to take that error, scale it by a gain, and inject that into my dynamics. Turns out I also have to inject in a boundary condition. And if you do that correctly, then your observer will converge. The state of your observer, which has the distributed temperature, will converge to the true distributed temperature of your system. Okay? This is a lot of what control theory is concerned about. Once I've done that, I now have an estimate of the internal distribution of temperature in my battery. Now I'm going to apply the diagnostic observer, which now adds this extra term here, where I have theta hat times psi, and I'm injecting some error here, but the other key part is I have an adaptive law that is trying to learn theta from the error. And the reason this works has to do with the mathematical proof. But the idea here is theta hat, when that's non-zero, that is going to detect the fault, and then the magnitude of theta is going to detect the size. So, from this, the key steps are we'll use control theory and Lyapunov stability theory to prove convergence of the system. And what this analysis tells us is that the error between the true temperature and the estimated temperature converges to some number epsilon. And also the size of the fault and our estimated size of the fault, this error converges to a different epsilon. And it turns out that I can make these two epsilons arbitrarily small if I pick the gains of my algorithm correctly. Okay, so those are the tuning knobs. If I pick them correctly, I can get this thing to converge. Okay, so that's the theory. Let's do experiments now. So what we did was we took a battery cell. Here's our battery cell in a cell holder. And to emulate a thermal fault, what we did is we attached a heating pad to it. That's what that thing is on the surface of the battery. And while it was operating, we just turned on the heating pad to emulate a thermal fault. Okay, so a little goofy, but just a way to emulate some anomalous behavior. And so here you can see the two cases. So the nominal behavior is in red. You can see it, heating up just because of charging and discharging. And then we inject the fault. That is, turn on the heat pad, and then you can see some, the heat's rising, but it's still not 60 degrees Celsius, right? So we may not think that this is a fault yet. Okay. So from this, we ran our algorithm. I actually have a little video of it. Okay, so what you're seeing on the top is an estimation of the fault size, and on the bottom is the surface temperature. And the dashed black line here represents what is the threshold beyond which we detect a fault existing. So you can see that we run this, and what's in blue is our estimated fault size. We inject the fault, I think it's at 45 seconds, and you can see that our algorithm is essentially capturing that something is happening. There's some internal heat generation. Let me highlight again that the standard thing people would do is just limit check. So 60 degrees Celsius, I've detected a fault. I don't even come near that. Yet something incredibly important has happened internally, and I can detect it, within seconds. All right, so that's enabling. Let me now summarize. So what I gave you some background on batteries, electrochemistry, some of the fundamentals. I try to convince you that these physics-based models, namely electrochemical-based models, can enhance monitoring performance and safety. I talked about this idea of optimal experimental design for parameter identifiability, aka the dim sum idea. I like dim sum, that's why we call it that. So anyways, then there's thermal fault diagnostics. There are other applicable control theoretic tools that I think are useful in this space. There are other research topics I didn't discuss. If you're interested, feel free to email me. Here's some reading materials if you're interested in studying more on this topic. And you can download the slides at this link. But with that, I'm happy to take any questions, and I'll just leave it on the summary slide here and take any questions that you might have.
So another system which we're trying to model extensively is climate. Can you say anything about your thoughts on discerning whether there's a human impact on climate? Because we're trying to ask the question: is there a impact? This may be completely outside the space, but it seems like there's at least some thermal runaway possibility.
Yeah. I suppose if I could definitively answer that well, and there should be some awards coming my way, and the answer is no, I can. I don't think I can, but the way, I think some things I'll highlight is, I'm operating here in a sandbox, at least in a sense that a battery is like a fully engineered system. And when we're talking about climate, we're modeling, not just the environment, but the people and their impact on it, for which there is not a good physical science that describes people. So the other thing I'll highlight is with this way of thinking, a key aspect is you really need a good model to separate uncertainty from anomalous behavior. So the fact that we have to model people and we don't know that well makes it really hard to deconvolve just the uncertainty of this system from what could be an anomaly, that is, industrialization of modern societies. So I think my overall thought is that we scientifically aren't there yet, and although it's not my area, I would say some of the key aspects would be how do we model society? If we can model that well, then maybe some of these concepts that I described today could come to bear. Yeah, what's your question?
So you showed that the model that you came up with was very, very sensitive to small changes in battery performance. How do those small changes in battery performance map to battery failure and the utility of the task? So is it always that if there's a small excess in the heat dissipation, that cell is on its way out?
So this example I showed of injecting heat was just one that we could test in a safe way in a lab setting. But there are, how should I answer this? There are a lot of things that you can do to batteries that will cause failure that are obvious and not obvious. So for example, if you charge super fast, it's fairly obvious that you're going to do things like fracture the particles in the material, cause excessive heat generation, and that can cause failure. If you overcharge it, that can cause failure. There are other things like if you charge a certain way at cold temperatures, it's maybe not quite as obvious how to do that. So for example, you live in Detroit and you travel somewhere for a week, you come back and your car's been sitting in the parking lot, it's basically an ice cube, you need to get home because you're tired, but your vehicle's out of battery and you charge it, you could actually create a lot of damage in that type of scenario. So yeah, I guess I don't have a simple response. But the key is the understanding the models and the physics to really deconvolve this. I'll say one thing in the optimal experimental design where we optimized the items of my dim sum menu. There were things that were maybe, I expected like these smooth profiles would be optimal. I don't know, because it would be optimal for exciting parameters. It turns out the thing to do to become sensitive to parameter variation was to basically charge and discharge it at super high rates back and forth. So it's like, my student would say it's like we're banging our battery with a hammer, and I guess that makes sense in the end.
When you made your formulation for your convex optimization, and you referred to it as similar to a knapsack problem, the knapsack problem is intractable generally. So, did you guys have to make some sort of, heuristic assumptions on that? Maybe I missed it.
No, that's good. You're calling me out for being being relaxed in how I describe this. And the answer is we made a relaxation.
Yeah.
So you can only pick integer values of items from the menu, and we relax this by allowing eta to be a number from 0 to 1. So that's how we do it, and then we just round that to take the fractional solution. So to be precise, we actually relax the knapsack problem to arrive at a convex.
So you guys made a continuous version and then
Exactly.
rounded it.
Exactly.
Thanks.
Invite our speaker again.